Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's biweekly contest, visit array positions to maximize score. The problem is very interesting and it is a very good problem to solve if you are trying to strengthen your understanding about top-down, how to optimize top-down solution or how to convert top-down to bottom-up solution and optimize it. This problem can simply be solved using a small observation in top-down solution itself. But as always, we would like to take this opportunity and discuss different solution of this problem. In particular, we will be looking at how to convert the top-down solution to bottom-up solution and then optimize the bottom-up solution as well. So we have done this multiple times in this channel in the past. If this concept looks new to you, I would encourage you to watch the video till the end, and then I would link some other videos in the description down below. You can try those problems as a practice problem or as a follow-up to this particular problem. So with that, let's get started. The problem states that you are given a zero-indexed array nums and a positive integer x. You are initially at position 0 and you can visit other positions according to the following rules. The rules are, if you are standing in position I, you can move to any position j which is greater than I. So in other words, you can move to any position in the right, but you can't go left. Then if you are at a position I, then you will get a score of nums of I. Now if you move from position I to position j and the parities of nums I and nums j differ, then you will lose a score of x. So with these conditions in the movement, you have to return the maximum total possible score that you can get. So notice that because you are starting at position 0 and it is given that for any given position I, you will be getting a score of nums of I. So you are already starting with nums of 0 score, right? So let's take an example. Let's say this is the given array nums 2 3 6 1 9 2 and x is 5. So we need to figure out what is the maximum score we can collect if we start at 0th index, which is 2. So as mentioned in the first rule, that we can only move to the right. So one such possible movement could be, you will start from 0, you will go to 2, and then you will go to 3, and then you will go to 4, right? So let's follow that. So you start from 0, let's say you go to 2. So if you go to 2, you will get a score of 6, right? And because parities of I, nums of I and nums of j are same, so parity of 2 and parity of 6 are same, basically both are even, so you will not incur any loss in the score. So you started with score 2, you get one extra score of 6, and now you are at position 2. Now they are saying that we'll move to 3. So if you move from 2 to 3, you will get extra score of 1, right? Now notice that because you moved to a different parity, this was even and this was odd, you moved to a different parity, you will lose a score of x. So x was 5, so you will lose a score of 5 as well. Now finally from 3 you can go to 4, and because they are of same parity, you will not lose anything and you will get an extra score of 9. So this is the total possible score you are getting in this particular journey, which comes out to be 13, and this is the maximum possible score that you can achieve irrespective of whichever paths you try, and hence the answer here is 13. So hope the problem statement is clear. Now how to solve this? So let's just try to simulate whatever is given in the problem. So we are starting at index 0, right? And now they're saying that you can move to any index j which is greater than I. So from index 0 you can go to 1, you can go to 2, you can go to 3, and so on and so forth, right? Now let's say you choose to go to 2, right? So just a random choice, you say that okay, I will go to 2. Now once you go to 2, what is the score you will be getting? So you will be getting an extra score of 2, right? Because you jumped to 2, right? And then you will be incurring a cost of x as well, because you changed the parity, right? So this is the total diff in the score once you moved from 7 to 2. Now once you are at 2, what do you want? You want what is the maximum possible score I can get if I start at this, right? So isn't this problem exactly similar to the original problem we are trying to solve? Original problem was what is the maximum score possible if you start from 0, right? And now the reduced problem is what is the maximum possible score if you start from index 2. Notice that this is exactly similar to the original problem and with just reduced constraint. The original problem says that this is the array and I am starting here. The reduced problem says that I am starting here, it means this is the array that I need to work with, right? So hope you can see the recursion here. So what will happen is, let's try to formalize it. From f of 0 you have various possible choice. So basically we need, our recursion needs a single variable. Let's say we have defined a function f which takes an index I. So this denotes that what is the maximum score if we start at position I, right? So if we start at position 0, what all choices we have? We can go to 1, we can go to 2, we can go to 3, and so on and so forth, right? So these are the possible choices that we have. Now if you go to 1, what will happen? The parity is same, so you will not incur any loss of x, but you will get an extra score of 9. So that's what you're doing. If you go to 1, this will be the score that you will be having. You will get an extra score of 9, and from 1 onwards you can just call this same function f to give you the maximum score possible if you start at 1, right? Similarly, if you go to 2, this will be the score that you will be having. Why? Again, we have discussed that already. When you go to 2, you will be getting an extra score of 2, but because the parity is changed, this was odd and this was even, you will also incur a loss of x. So this will be the total score that you will be having if you go to 2. And similarly, these are the scores you will be having if you go to 3, 4, 5 or 6. Now among all these scores, you can simply take the maximum one and that will be your final result. Or basically you will say whatever is the maximum score possible if I start at index 0, right? So just replace this 0 with I. This will become I plus 1, this will become I plus 2, and this will become I plus 3, and so on and so forth, right? So we can simply formalize this recursion in the following way. We can say that we'll start with index, right? And we'll try to find what is the next index that we are jumping to. So next index could be anywhere between index plus 1 to n. Now if they are of the same parity, then I will incur a loss of x, otherwise I will not incur any loss. And I will also be getting this nums of next value as my score as well. So this will be the total score if I decide to jump to next from the current index IND. And we can simply take the maximum across all such score, and whatever comes out to be the maximum across all possible movements, that will be the result of f of index, or in other words that will be the value maximum score that you can get if you start an index, right? Now what is the time complexity of this entire algorithm? Notice that time complexity would simply be number of times or number of unique ways you can call this function, right, multiplied by the time complexity of evaluating each state, right? Obviously we are assuming that we will doing memoization so that we will not compute the same state again and again. So there will be memoization code somewhere here which will just check one static array, and if f of index is something that we have already calculated, we will return the value from that array instead of recomputing it, right? So the complexity is simply how many unique times you can call this function. So notice that there is only just one index, and index can take any value between 0 and n. So number of unique ways you can call this function is n, right? Now for each way you are iterating over the next index and doing some constant operation inside. So you are doing order an operation to compute the value of each state. So in total, the complexity of this entire algorithm is order n square, again assuming that you have done memorization already. Otherwise, it will be exponential. Now, surely this will not pass the given time constraint because nums dot length is 10 to the power 5. So n square will not pass the given time constraint, and we need to optimize this. Now, from here, there are two possible choices. Either you try to come up with some observation in this top-down recursive solution itself and try to optimize it, or if you are not able to come up with any optimizations here, the very straightforward way is to convert this to bottom up and then try to think of optimizations, because optimizations on a array is much more straightforward than optimization in a recursive function, right? So we'll look at both the ways. Let's start with the recursion first, right? So we have this particular function and we need to optimize it. So we had two things, like we had n square, right? The first n comes from the fact that we have n number of ways to call this function, and second n comes from the fact that we are iterating over n indexes inside a single state. So clearly we can't avoid the first n, or in other words, we can't avoid calling this function at least once for each of the indexes, because that's the minimum that you can do if you are doing a recursion. So we have to optimize this for loop somehow. So we need to remove that order n from here and introduce order log n or order 1 complexity somehow, right? So one way to look at it is, see what you are doing here. You are saying that I will be iterating over the next, and what all things are dependent on next. This value depends on next, right? This value depends on next, and uh, once you calculate this value, you can simply get this value as well. So I am not taking this particular value. So we have three expressions that depends on next. So if you want to remove this next, what you can simply say, I will take care of these three expressions further in the recursion if I can take this state with me, right? So instead of figuring out everything for next here, what we are saying is we will carry over whatever is required from current index to the next index, and we will compute everything in the next when next index turns come, right? So in other words, what we are saying is we will take the value nums of index modulus 2 further down the line and make sure that whatever we wanted to compute with this value will be computed afterwards, right? So let's take an example. Previously what we are saying is, if we are starting from here, I will try to find out what is the next possible index that I can jump to. So from 7 I will jump to 2, and then I will call f of 2 to get the result of the further down the array, like this part of the array, right? Now instead of saying, like, if you are doing this, then for sure you need to iterate over all possible next uh, indexes, right? But instead of saying this, what you can simply say, I will start from here, right? Now I will not say where will I end. Instead I will say, okay, I have started my journey here. Whatever this number has to contribute is something that it has contributed already. Now at every index I will go and see if this can be an ending index of the already started journey or not. So basically you have started your jump from 7. You will say for each index whether the jump that we have started previously is ending here or not. So if it is ending here, then you can simply compute whatever you wanted to compute previously. If it is not ending here, you will simply move forward to the next index, right? So the modified algorithm would look something like this. You will, because you need to have parity to determine this particular expression, we carried forward the parity as well. So instead of only indexes, we now have index and previous parity. Now we are saying that there is a jump which we have started somewhere before, and the place where we have started the jump has this particular parity, right? Now at any given index I, two things can happen. Either the jump that we have started will end here, or it will not end here, right? That's just too simple thing. So if the jump will end here, what extra contribution you will get? You will get this value, right? And then you will get minus x depending on whether the parity was same or not. So you already had the parity of the index where the jump was started. So you can simply maintain that parity and say whether you have to subtract minus x or not if the jump ends here. So that's what we are doing. We are simply checking two conditions, where whether the previous jump that we have started will end here or it will not end here. So if it is ending here, what you are saying is a jump ends here, so next jump will start from here and will continue. So what you then need is, this is the new starting index of the jump. So you just updated the previous parity to the parity of the current index, and you said that okay, I will start the jump from index. Now give me what is the maximum possible score I can achieve from this particular index. And as discussed, you will also be getting a contribution of nums of index. Also there would be minus x depending on whether is same parity is true or false. So if it is false, there will be minus x as well. If it is true, then there will be no minus x. So based on this, you will compute one possible value of result, and second possible thing is you will not end the jump here, so you will just move forward. So basically you are saying that this jump will now continue, this will not end at 2. So in other words, what you are saying is, I will start, or I will try to end the jump at somewhere at index plus 1. Now because we haven't concluded the jump here, the parity of the previous number that we have taken is still the one that we have get into the function. So we just simply pass that forward, right? So with just one observation, that we just need this particular thing inside this function about index, and if we forward this thing to the next indexes, we can simply compute the same things when we are visiting next indexes. So we don't need to recompute this particular part again and again, and that's bring down the complexity from order n to order 1 inside this particular state. But there is one more addition. The number of states previously was n, but now it will be 2n, because uh, each state can have, like, number of different parity can be 2. So each index can be called with two different ways. So the overall complexity is still order n, and it is enough to pass the given time constraint. So I'm not showing you the code for this. I would encourage you to pause and try to code this entire thing by yourself. Next we'll be looking at, what if we are not able to make this observation. Let's say you somehow is not able to think of that, okay, I need there is a way to remove or to carry forward this, and then we'll be able to reduce this complexity to from order n to order 1. In that particular case, as I have mentioned, the first thing that you should try is convert this top down solution to bottom up solution, and then think how to optimize that bottom up solution, because optimizing array again is straightforward than optimizing the recursive solution itself. So next we'll be looking at how to convert this top down solution into a bottom up solution. So we have discussed this multiple times in the channel in the past. So if you are following this channel for some time now, I am very confident you will be able to convert this top down solution to bottom up solution by yourself within minutes. So I would encourage you to pause and try to come up with that by yourself. So hope you have thought about it. So this is the simple way to convert any top down solution to bottom up solution is, you will start from the base case, right? So the only difference between top down and bottom up is, in top down you don't care whether the next state that you will need is computed or not. You will just call the recursion and the recursion will take care of it. But when you are doing bottom up, you want, like, you will not rely on the fact that next cannot be the next is not computed. You will simply say that if I am doing something for index and I need some next, I am very sure that all the next that I need is already computed, right? So that's the simple formula. Now, to make sure that we will start always from the base case, basically we need to start from some index for which we know the answer already. So for index n, or basically index after the last index, we already know that there is no possible move at all. So the value for that is 0. So we will simply start with f of n as 0. Now after that, we will simply go backwards as we go in the top down solution. In top down solution we are going forwards, so because we are going forward in top down, we will simply go backward in the bottom up. We'll say we'll start from n minus 1 and go all the way to 0, right? And for each indexes, the computation is exactly similar to what we have done in the bottom up solution. So notice that this part is exactly copy paste from the top down solution itself, right? So hope this particular conversion from top down to bottom up is clear. Now we need to like, this solution is also order n square. Just to highlight that fact, we are, like, here it is very simple to argue about, because we just have one for loop here, and inside this for loop we just have another for loop inside which we are doing some constant operation. So this solution is also of order n square. So we need to optimize this as well. Now think of how we will optimize this. So again, we will try to optimize this particular inner loop itself, because it doesn't make sense to reduce on the outer loop, because we need to iterate over every index at least once, right? So that's why we'll have to figure out how to optimize this particular thing. In other words, we need to somehow make sure that we get the maximum that we want across different indexes in just order 1 time, right? Or order log n time, or whatever is less than order n. So this statement that you need a maximum across all the indexes after current one in constant time operation is sufficient to hint toward something like suffix max or prefix max, right? So I would strongly encourage you to pause and try to think of how to optimize this particular for loop in order 1 complexity by yourself. So hope you have thought about it. Now the solution is straightforward. We need to optimize, or we need to remove this loop. Now what this loop is doing, let's try to iterate over that. Let's say this was the array nums 7926549, and we are trying to compute the value of array f, right? So let's assume that we have already computed the value of f for some of the indexes. So value of f for index corresponding to 9 is computed, corresponding to 4 is 5, corresponding to 5 is 9, and now we need to compute the value of f at this particular index. Now what will you do? Let's look at this for loop itself. What this for loop will do, it will iterate over all the next indexes, will check if the parity is same. If the parity is same, it will simply subtract minus x and also add f of next plus nums of next, right? If the parity is not set, it will not subtract x, and it will just add f of next plus nums of next. So let's look at that. I will iterate over all the next indexes. So we'll start from this. So this particular thing, if you look at, the parity of 6 and 5 are different. So because the parity is different, you will be getting a contribution of -4, right? And what is the contribution of this particular thing? F of next plus nums of next. So basically 5 plus 9, which comes out to be 14. So from this particular index, you will be getting a contribution of 14 minus 4, right? In the same way, if you try the next possible index, this one, you will be getting a contribution of 4 plus 5, right? and because the parity of 6 and 4 is same, you will not be subtracting x anymore. So the value of x is 4 here, right? So you'll not be subtracting x anymore, and hence the parity and hence the contribution of this particular index is 9. And finally, for the last index, you will do the same thing. You will get a contribution of 9 plus 0, which is 9. And because the parity is different, so 6 is even and 9 is odd, you will again be subtracting minus 4 from this particular contribution as well. So you will take the maximum across all three, and whatever comes out to the maximum, that will be the value at this particular index. So in this particular case, the maximum is 10, which is 14 minus 4. Now you need to optimize this particular thing. So you need to get this maximum in order one time. Now how to get this maximum? If this minus 4 would not have been there, let's say there is no, this expression is not there at all, then what will you do? This is straightforward, right? If this expression is not there at all, what you need is, you need the maximum across the suffix, which can be easily achieved with a suffix max. You can just take the suffix max, you can maintain suffix max as well while going from left to right, and for any particular index you will just look at the suffix max, and that will be the answer for that particular index. But the situation is bit different because we have this expression as well. So we need to subtract something based on whether the parity is same or not. Now notice that because of this condition, a single suffix max would not work, because this subtraction is something that is dependent on the current index. And because when you are computing, let's say, this particular index, you don't know what will come at any index before me, and because you don't know that, just a single suffix max will not work. So that's where one possible thing could be to just think of how many different ways are there to, like, how many different values that you can get from for a single number. So for this particular index, or for this particular expression, you will get only two things, either even or odd, so either 0 or 1. So instead of maintaining a single suffix max, you can say that I will maintain two suffix max. One when the numbers are odd, so one suffix max will contain the maximum across all the odd numbers, and another suffix max will contain the maximum across all the even numbers, right? Now once you have this, then then considering this particular expression is also straightforward, right? How? Let's look at it. Let's say you maintain two suffix max already, so you have this two new array with you, which the first one denotes the suffix max of all the odd values, or all the odd indexes, sorry, all the odd values uh, in the given array nums, and second array contains the suffix max across all the even values in the given array nums. So if you look at it, the suffix max would be 9 plus 0, 9. So this is 9, right? Now this was even, so even though it is 9, this 9 will not be contributed. So let's say this was not 9 and this was 19, just for an example. So even if it is 19, this value would be 9 itself, because you will not take this particular element into the odd array, because this element is even, right? So because it is even, you will not take the contribution of this one and simply copy the value from the previous index. And after that, notice that this 5 is even, sorry, this 5 is also odd, so you will take this particular, take the contribution of this particular number as well. So you will now have a maximum of 14. So you will say the value here is maximum of 14 comma whatever the maximum I already have, which is 9. So maximum of 14 comma 9 is 14. Now in a similar fashion, you will contribute, or you will compute the value of even array as well. So notice that we'll start from this particular index, and because this is even, or this is odd, you will not contribute this to the even array at all. So we didn't contribute this 9 here at all. Now second, this 4 is even, so this will be the contribution of this 4 will be reflected in the even array, so we just reflected that in here. And finally this is again odd, so this contribution of this particular index will also not be there in the even array. So this, even though the value here is greater than 9, 14 is not the value here. Here it is still 9 because you are only taking maximum across even numbers. So once you have this, then how to compute this particular value? So again, this is very straightforward now. I would strongly encourage you to pause and try to think of this piece by yourself. So notice that what you wanted is you are subtracting something from, you are subtracting x from the maximums if the parity is not same. So let's say the parity of current number is even. So here the parity of current number is even. So because parity is even, if you take or if you land on a odd number, on any odd number after me, the parity will change and you will be charged minus x, right? So what you will say that, okay, because current parity is even, if I took the largest value of odd, I will take that largest value minus x. So this contribution of this, or the best that you can get by landing on an odd number, is 14 minus 4, which is 10. And similarly, the best contribution you can get by landing on an even number is 9. Notice that with 9 you don't need to subtract x because even number and even number parity matches. So x subtraction is not be there. So for every index, what you will do, you will just check whether the current index is odd or even. If it is odd, then you will not subtract anything from the odd one and subtract x from the even one and take the maximum. If it is even, you will subtract x from the odd one and take the maximum of odd and even. So let's look at the pseudocode. So this entire thing, this computation can be done along with the computation of this f array itself. So finding out what is the maximum odd or maximum even is just order one operation. So this entire loop will then go away and we will have a simple order one operation based on whether the current number is odd or even. So the pseudocode for the same would look something like this. As discussed, we will just check whether the current number is odd or even. If it is odd, then we, like, current number is odd. So if you land on a odd number, you don't need to pay x, right? So that's what we have done. If we land on a odd number, we don't need to pay anything. So the maximum value of any odd index is something you can consider directly. But if you land on a even number from here, then you are changing the parity, and because you are changing a parity, you will be subtracting minus x from here, right? I'm sorry, there will be plus. So this will be the value of f of index. Now notice that you need to update the suffix arrays as well. So for, if the current element is odd, the even array would not be modified, it will stay as is, right? But if the current element is odd, then odd array will get its contribution. So for, you will just update the odd array to odd of index plus 1 and f of index plus nums of index, right? Similarly, if the current element is not odd, instead it is even, so this particular element is even. So in this case, if you land or if you jump to an odd index, then you need to contribute minus x, or you will be incurred a cost of minus x. So that's what we have done. If we go to an odd index, we will be paying minus x as well. But if we go to an even index instead, then that will, because the parity is same, will not be incurred any extra cost, and the value would simply be even index plus 1. Now finally we need to update the odd and even array as well. So again, the current element is even. So because the current element is even, there is no contribution to the odd suffix sum, suffix max, so it will stay as it is. And to the even suffix max, you will just do a max over the previous value and the current value of the index as well. So notice that with this just simple suffix max approach, we are able to reduce this entire thing to just order n. Now one small optimization you can do here is notice that you are only dependent on odd of index plus 1 and even of index plus 1. So you don't need to maintain this entire full array. Instead, you can just maintain a single integer and that should be sufficient. So you can completely get rid of this array, just maintain two integers here. And in the similar fashion, you don't need f of index anything apart from f of index plus 1. So you can get rid of this entire thing as well and just replace it with single integer. So with bottom up, you are getting like you can replace this arrays with a single integers, and the space complexity in bottom up can simply be order 1, or it can be reduced to order 1 very easily because you don't need to maintain the entire array with you or store the entire array with you. So the space complexity will be order 1 and the time complexity is order n. So hope this particular solution makes sense. Just to reiterate over the main part was to look at the entire thing without this expression first, and if you look at the entire thing without the expression, it is very clear that it's just asking for suffix maximum. Now with this expression, there are two possible choice here. Either we have to subtract minus x, or we don't have to subtract anything. So for that particular thing, we just maintain two different suffix max, odd and even, and based on what is the parity of the current number, we will subtract minus x from one or the other, right? So I would strongly encourage you to pause and try to code the solution by yourself. I would encourage you to code the order 1 space complexity solution as well, because that will give you much better understanding of how things are working here. So next we'll be looking at the code. So again, hope you have tried this at least once by yourself. So this code is the one that we have discussed, that we can reduce the complexity to order 1. So we haven't maintained this odd or even array per se. Instead we maintain this max order, max even. And what we have done, we just simply figured out what will be the value if we land on an odd index and what will be the value if we land on an even index from here. So if the current number is even, then we don't need to subtract anything from even, and from odd we just need to subtract minus x. In the similar fashion, if current number is odd, we don't need to subtract anything from odd and we just subtract minus x from even. Now finally we know what will be the value of the current index, so we can simply update the value of max even and max odd based on which what is the parity of the current integer. So one small difference between this particular code and this particular pseudocode is this particular pseudocode takes the value at the end. So basically this f of index doesn't consider nums of index at all. So nums of index you need to add by yourself at the end. So the answer when you return from here would be f of 0 plus nums of 0, right? But in this particular algorithm we have also taken the contribution of nums of j directly here, and because of that we'll just simply return we don't need to add n of 0 at all. The answer would simply be f of 0, and f of 0 would be either max even or max odd based on what is the parity, right? So hope this entire solution makes sense. If you have any doubts in any of the two solutions that we have discussed, feel free to post them in the comment section below. I will be able to answer. Again, this approach of converting a top-down solution to bottom-up solution and then optimizing the bottom solution itself is will help you in lot of different problems as well. We have solved multiple different problems in this channel already. I will try to link them in the comment section below or somewhere in the description below. Make sure to check it out and try to solve those problems as a follow-up to this problem. So hope you enjoy the video. If you like it, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.